Yep, looks looks good.
All right, awesome. Yeah, thank you for joining today and listening to me. I'm Andrew Bennett. I'm an assistant professor at the University of Arizona, and this work is in collaboration with Oriana Chegwidden at CarbonPlan and Nicoleta Cristea at University of Washington, who really, Nicoleta was the person who sort of spearheaded this as the tutorial that it became. And the sort of idea behind it was to improve some machine learning education and making it completely open and accessible. So I'm not sure how many of you have tried to do machine learning with your real data, but a regular problem for earth scientists is they see all of this deep learning stuff and they try to, do the little tutorial and it's on the handwritten digits or whatever. And, then they're like, great, I learned it, but like my real data is way different than that. So I don't really know how to translate it. And so Nicoleta and the GeoSmart team were the people who sort of kickstarted this. I'm not actually a part of the GeoSmart project. I just kind of hopped on to develop a tutorial, and I've been interacting with them ever since. But GeoSmart is an NSF-funded project that sort of offers open source curriculum for advancing machine learning in the geosciences. And so they have all of this open curricula. So there's sort of three different examples of Jupyter books from classes that various partners have taught. There's a couple more if you go on the website. The link is right there, and we'll have it again at the end. And in addition to that, so those are like textbook sort of like, week by week lessons that you could use in a class. But they also came up with all of these use case books, of which one of them is the one that I'm going to show today. And so these are more like project-based sort of demos, things that you can run to see how real work gets done in geoscience, machine learning world. So just to jump right into what I developed alongside Oriana and Nicoleta was this workflow that's sort of shown on the right, where the basic idea was to take Era 5 reanalysis meteorological data and the Era 5 land snow data and basically train a machine learning model that will take you from the meteorology to predicting snowpack. And then once you have sort of the trained model that comes out, you can apply it to downscaled CMIP6 climate scenarios to better predict future snow. So that was sort of the idea. So this is like a non-trivial sort of use case. It's something that is more akin to real research. And actually, it is real research. I'm still working on getting a paper published on this. That's more like scaling this up. But we sort of, in putting this together, identified these lessons that we think are sort of standalone things that people need to understand. So first is data preparation, as I mentioned. That's actually ends up being, I think, the longest tutorial in the whole thing. And then taking you through how do you, you've got your data, how do you train it? Okay, you've trained your model. How do you like actually evaluate it and rigorously understand, preventing data leakage and tracking your experiments, things like that. And then finally, this question of downstream tasks. So most papers that you see sort of published in machine learning world kind of end at step 3. But a lot of stuff in our world, we want to actually take and do something in the world. So like being able to deploy your model or use it on sort of incoming data, it might be a little bit different. So these are the 4 things that we really wanted to focus on. So building the tool chain was not a trivial task. And so we originally based this all off of access to Microsoft Planetary Computer, which has been pretty great. The only downside is some of the resources were offline for a while. Maybe not offline, but definitely when ChatGPT came out, it became extremely difficult to get one of the GPU instances, which sort of made this tutorial not very usable anymore. Luckily, that's changed. But so this can run if you have your planetary computer login, you can actually run this all on your own with all of the data in the cloud and all of that, which I'll talk about. So as I'm here at Pangeo, the Pangeo ecosystem for dealing with like NetCDF, ZAR, all of that type of stuff through X-Ray is really excellent. It's saved probably huge amounts of time and advanced a ton of science. And same for the PyTorch ecosystem. It's really usable, user-friendly, easy to understand. The glue between them is still somewhat challenging. And so there's some nice packages that we use that I know have been presented on here. So like the XBatcher and Zen3Geo both are used in this project, basically to go from that gridded data sets in X-Array to PyTorch tensors that can be put on a GPU and run. So this is all based on tons of open tools and has been like a really good showcase for how to put them together. I will say that the infrastructure at the hardware level is still a challenge. It's still not quite clear the best way to put sort of these resources in the hands of students and practitioners without them having to either pay money or jump through a bunch of hoops. So like planetary computer, you have to sign up for and have a valid use case. Things like Colab end up not having all of the background libraries that you need, so you have to put together all sorts of stuff. So that's still something that I think is a challenge. But with that, we sort of ended up with three things. So the set of tutorial notebooks is really the product, but I think we got a better understanding of like the challenges for actually like making this accessible to the world and being like, hey, you can go and run this without having to do a bunch of setup. And I think, in the months since this was sort of put out into the world, there's definitely an appreciation for the speed of the AI ML development landscape. Some of the things that we used that were cutting edge at the time of development are no longer like in development. So that's something that keeping this up to speed is going to be a challenge, but hopefully it provides value in the short term. So just to jump through sort of what this looks like, and if we have time, I could show the actual notebooks, but I didn't want to just like shift enter through a bunch of stuff. So the data preparation notebook really deals with how to deal with like stack catalogs and intake. How do you use like FS spec and understand how to access cloud-based data sets? So everything is in Azure Cloud Storage. And then building workflows on like atomic operations that you implement as little functions. So you start out with like a data set that's global, and because this is a tutorial, we just subset out this Western North America region, although you can run it on any of these sort of little named regions in the upper right. So like what's the base case for getting just a region out of this? How do you stack it into a sample dimension which has multiple variables? Things like that you do in your machine learning workflows that aren't really well documented in scientific literature. And also really focusing on iterative development and developing workflows. So we sort of always go like, okay, what's the next step? Okay, how do we roll that back into the overall workflow? So by the end of it, there's just one function that gets exported to a Python module, and that's the function that you call to get your data loader up and running. But behind the scenes all of the steps you took to get there. So this was really, I think, the part that I think goes swept under the rug. So I hope that this is a really valuable piece for some people getting up and running, because doing sampling out of these large data sets can be sort of confusing, I think, to geoscientists. And then let me check chat here. Okay, great. Yes, Xbatcher is part of the stack, just to answer your question there, Ryan. So then we go into model training. So you've got your training data pipeline, and then basically trying to help you understand how to adapt it to a common recurrent neural network, which is this figure on the right. So it's like a time series based model. And we also start thinking about like, how are you going to train this, validate it, and be rigorous about it early. So we start out with developing, it's not just like shove it through the notebook and hope that all of your figures come out. We save everything out. And then finally in the third one, we actually go, okay, now you've trained your model. Now you can start looking at its output. So this involves basically taking that understanding of how to build the model and using it in sort of this modular way where you save out your config here down the bottom, load it in, and then can start to run it on your testing data. So we show how you look at that against time series mode. So the orange line is the model, the blue line is the truth. This ends up being a pretty good model. We were actually pretty surprised at how well you can do with small resources. And we also look at sort of differences in like the peak snowpack across the region. So while this is like still subsampled from the global data, it's a pretty like hefty amount of data, I would say, for most sort of tutorial-like things. And so just going to the last part, so now how can we actually use this to gain some understanding of a real scientific sort of application? And so what we do is we take the trained model and we pull out some downscaled CMIP6 climate projections. These are provided by CarbonPlan, and we actually run the trained model on it. And so we can look at going into the future. This is maybe the snowpack evolution for the 20s, showing some sort of range across a 30-year period. And then going out into the future, you can really start to see the decline in snowpack. And you can look at where that occurs, and you have to sort of squint for a while, but it mostly happens around sort of the edge buffer zone. So like where the snowpack was sort of shrinks spatially, and that's where a lot of that is going. But as far as the tutorial goes, there's a lot of open questions around this, and archiving the code or the data and compute is still sort of the thing that we kind of developed this and put it out into the world. But at some point, GeoSmart will end, and my time will be moving on. So it's sort of an open question how to maintain this for the very long term. But this is, I think, a really cool way to do full end-to-end from opening the data to deploying it on new data across the board. So that's really all I have for this. I can show the tutorial. I can kind of show you what it looks like in notebook form. The QR code will take you there. Again, feel free to email me with any questions or thoughts, and I can take some questions in the meantime.
Do you want to actually just how about showing your notebook a little bit, and then we could take questions, maybe, just so then we can include that in the recording.
Yeah,
that's okay.
Yeah, that's great.
Yeah.
So
can you make that a bit bigger?
Yes.
Yeah. Okay. Cool.
And oop, I'm in the wrong spot. So how's this?
That's great.
Okay. To the top. So I'm actually going to bump this over also, so we don't have figures that are too huge. So again, I'm running this on Planetary Computer. I start out with, just like, hey, what's going to happen in this notebook? I give a shout out to all of the packages that are really, crucial behind the hood, things that are really doing most of the heavy lifting here. The Planetary Computer comes with most of them. There's a couple small packages we have to install, and I don't know exactly why Pip was yelling at me. It installed just fine. This is all, again, runnable. So as you can see, there you go, imports everything. It kind of follows their standard workflow. And we start out, opening the data. So we've got the stack catalog, which is the ERA 5 data. This part is hosted by CarbonPlan. And we can look through it, try and understand what variables are in there. So the three that we use are daily, max, and min air temperature and precip, and those go in to the model. I also just show, if you want to see where the actual data is. Like, I'm trying to sort of build up an intuition of how you can use Stack more generally beyond just this notebook. It's not like about like, okay, we got to get to the model as fast as possible. We want people to be able to experiment a little bit. So as usual, you just end up with sort of a big X-array data set, and that's got all of our variables in it. Same thing for the snow data. This snow data is actually hosted on a different, this is the ESIP tutorial Azure bucket, which is actually a personal one of mine. So it's maybe poorly named now, but so we pull in that data, and I'm just going to sort of go through and show. So at the end, I'd go through and talk about, okay, this is how you get it all in one go. And now the question is, how do we actually get it ready for machine learning? So then we have to walk through like, okay, why do you need to sample your data? And like, what's a way that you can sample it? So I should give a toy example here first of like, this is how this data pipe thing works and why you want to use it. And then we finally bring it back to our full data set where we start to do things like subset out the region. That's, pulling it from the global to just a small section where, we talk about how you do that. Okay, we implement that in the workflow, and then slowly build this up with small functions over time and I know I'm just scrolling over this, to at the end, basically, this is your entire data pipeline that you do. So you open up a data set, you get it, you use XBatcher to get small pieces of it, you filter out missing data, you transform it, and then you convert it to a tensor, and then that's your data sampling process. And we just wrap that all in one thing. And if I go back here, here we go. I'm not going to go through all of them, but so once you have this, what we do is we sort of roll it forward. And so in the second tutorial, we talk about how we actually do the training. And one of the things that we make clear is, hey, putting all of your code from the last notebook into a module means you can just import it, and you don't have to keep track of, in like 4 different notebooks. If you change one function, make sure you keep it up to date. So we just use that. You pull in your data, we're just calling the merge, and then we sample from it. And then we talk about the model structure, go through some of the equations, how the model works. And notably, we talk more about things like, hey, how do you get your data into the model anyways? So like how to format the batch, time steps, targets, dimensions, and what they mean. We do some like little pre-process, or rather this is post-processing, a little custom piece to just pull out the data that we want. And then we, workflow it out into a function that will let you, now you could, keep track of all of your hyperparameters, which would be these sort of function arguments. And so we do that. We do a training. And then the last thing that I want to show, is this what we call a very light introduction to MLOps. So like if you wanted to actually keep track of this and be rigorous, you probably want to put things in a configuration file where you log things like, hey, what regions am I actually training this on? What are all of my model hyperparameters? And then we provide a way to save and load those so that you can basically, if you wanted to put this on your own hardware and run like a big hyperparameter sweep, you could do that, and it's now sort of tractable. We allude to some other tools that are out there, but we kind of make it bespoke here just so that people really understand what's going on. And so that's where I'll stop this. The other notebooks are you know, if you want to run through them, you're welcome to, but this is the flavor of it.
Well, that was awesome. Wow. Thanks so much. I'm going to stop the recording.